I'm going to be pacing a little bit everywhere, but essentially what I want to talk today, as Ingo mentioned, is about, the combination of requirements with learning. And essentially the reason why I would start to tell you by why do I think this is important, actually, as a problem for us to look at. And the reason for that is essentially why comes from the fact how learning has been used recently to design systems, essentially how learning got to systems. And traditionally, I'm an electrical engineer, so when I look at engineering of complex systems, I look at the system engineering cycle, which would have engineers starting by setting requirements, collecting data, developing models, and then optimizing operational systems, right? And most of the work that I have done over the past, let's say, 7 years has been to, incorporate requirements throughout different steps of the system, right? Either by adding budgets to experiments when collecting data, or risk aversion when creating models for estimation, or inducing resilience into controllers, right? Now, as these systems have grown more complex and more intricate, right? This engineering cycle has become very costly now and more difficult to go through. And the promise behind learning is that actually it could take us from data to operation with little to no human intervention, right? This is a promise that is becoming an emerging reality, essentially, as learning has become the core technology behind a lot of applications, from photonics all the way to healthcare. And the main thing behind, let's say, the success of learning has been empirical risk minimization, so ERM. Now, ERM is just an optimization problem that fits models by minimizing an average loss over data samples, right? This is an idea that is at least 200 years old in statistical inference, right? It's the basis of what Gauss was doing to fit planetary orbits. Now, the thing we know is that, linear regression doesn't drive cars, so there has to be something slightly different happening behind that. And it turns out that the thing is not really with the tool, but with how we use it. And over the past 50 years, there are essentially 3 breakthroughs that took us from, let's say, ERM before to what it is today. And the first one is the one that inspired most of the research that I have been doing recently, which is the development of learning theory. So around the 1970s, 80s, a series of work have essentially shown that the ERM problem is a little bit more than what we were doing. It's actually a solution of a statistical problem. So there's something like the law of large numbers that happened here, that the solution of this problem fits not only the data we have, but also generalizes to the whole population, right, under certain conditions. That combined with, the advent of the internet and deep learning that gave us a massive amount of data to learn from, and also tractable, flexible parameterizations to learn with, made learning made this success of learning this reality that it is today. Now, behind the successes lie also a lot of problems, right? They lie models that are prejudiced, biased, and prone to tampering and unsafe behaviors. Right? So over the past 10 years, a lot of work has been done to try to overcome these shortcomings by essentially investigating and improving each of the pieces of the ERM, from the generalization properties of the parameterization to properties of the data, of the losses that we are using, and as well as the algorithms that we are actually using to solve this problem. Now, in contrast, what I want to try to argue to you today is that there is absolutely nothing wrong with the ERM, and there is absolutely nothing wrong with learning. It's just doing exactly what we ask for, even though it's not what we wanted, right? So we're in the German tale of Faust that, made a deal with the devil to use its powers as he wishes, only to end up ruining his own life. So our problem here is not that we need to spend more euros or engineering in order to learn better. What we need to do, to ask ourselves, is how can we actually change the way that we learn? And if we go back to the engineering cycle, I would argue that the thing that is missing is very clear, and it's requirements. So essentially, we need to move from the current learning paradigm of just minimizing losses of the ERM paradigm to one where we learn under constraints. And if you only remember one slide from my talk, after this you can just go to sleep, it's okay. And it's not because it makes it look like I read Goethe, that's not the point, is that this is exactly the point that I'm going to try to make for the rest of this talk, okay? So today I want to convince you of 3 things. Essentially, that constrained learning is the right tool to learn under requirements, and that, it is a problem that is simultaneously hard but also tractable, that we can actually do it. So let me start with the first point, and this is a good moment for me to just stop and tell you, please feel free to interrupt me at any point if you feel that you want to ask a question or absolutely disagree with whatever I'm saying at the moment. So, okay, maybe the disagreement, you can keep it for us later, yes, offline, but I mean, whatever. So let me start with my first point by essentially presenting two constrained learning problems, right? Two constrained learning problem application, starting with one which is closer to my background in engineering, which is wireless resource allocation. So the problem we want to solve here is that of allocating transmit powers for different pairs of transmit receiver in order to guarantee that we achieve a certain communication rate, which means a certain transmission of information between these two, the transmission and receiver pair. So communication rate here is going to be the requirement that we want to achieve. Now the defining property of wireless communication systems is the received power. And among other things that it determines the communication rate that we can actually achieve over that channel. So this is the thing that matters to us, is how much power do we get at the receiver. And that's determined by essentially the how much power we input in the system and the channel that we have. In wireless communication, the challenge is that this channel actually varies somewhat randomly over time due to interference patterns. And that provides us with the difficulty that very often this channel is a phenomenon called fading. This channel essentially disappears and we have absolutely no chance of transmitting any data across. But it also provides us with an opportunity because every so often the channel is much better than average. So the way we want to exploit this is by actually changing the power that we input into the system depending on the channel that we actually see. Right? And we want to do that in a way that would, in a sense, guarantee a certain long-term average rate, which is actually how we experience the communications on the cell phone, right, or when we are using that channel. This is a problem that is quite easy to solve for a single transmit-receive pair. It's one that it has a closed-form solution, in fact. Right? Things become much more complicated when we need to account for interference between them. So I can put a lot of power into a T1 to guarantee that it transmits enough energy to RM1, but then it will ruin the channel of everybody else by increasing the noise. So this problem is one that is considerably harder, also because we typically don't know the statistics of the channel. We don't exactly know how this channel evolves. It's very application dependent. We have a lot of models for them, but in general, this is not something information that we have. That turns out to be exactly the situation that we have in learning, and we can just replace that, by samples of the channel that we have. That's an example. If at that point I just write this power allocation as as some parameterization of the power allocation, we recognize this to be exactly a constrained learning problem. So this turns out that wireless resource allocation is not an application of constrained learning. It is a constrained learning problem when written in this way. And because of that, we can use a lot of techniques that I will discuss later today to show you that we can, in a model-free fashion, approximate for small networks solutions that exist today, which use knowledge of the channel in order to be developed. And in large networks, we can actually provide much better performance than you would achieve using WMMSE, which is a weighted MMSE, is an approximation of the solution of the problem that I was talking about before. Now, obviously, I don't want you to think that this is the only thing we can do with constrained learning. So to try to convince you that there are other things that we can actually achieve with this, let's look at a problem that is perhaps a little bit closer to machine learning in general, which is robust image recognition, more of a vision problem. So here, the problem we want to solve is that you give the image of a cello to a computer and have it recognize that it's actually a cello. Right? This is something that we became extremely good at solving. We can take an off-the-shelf model and just hit above 90% accuracy on typical benchmarks of this problem. Right? The issue with the solutions we get is that they are extremely brittle. So we can make very small changes to the input that are essentially invisible to the naked eye. This too looks absolutely like a cello. However, the accuracy will drop from above 90% to essentially 0. So the problem we want to solve here is not really that of learning an image classifier, right? But it's that of learning an image classifier that is robust to input perturbation. So robustness now is going to be the requirement that we want to impose. The typical way to do this nowadays is to use a technique known, or let's say the most effective way we found so far to do this, to use a technique known as adversarial training. This is a technique based on old solution from distributionally robust optimization, or robust optimization from the 70s, where we're going to replace the objective function that we have here by what we call the adversarial, or the adversarial loss function. So rather than measuring our performance on clean data, we're actually going to measure our performance on data that has perturbations in it, right? And not any perturbation, but the worst case possible one that we could find around. Right? This is a technique that is extremely effective at taking classifiers that have large, let's say, that have low robustness and making them robust, right? There are essentially two issues with this approach. The first one is that we actually have to find those worst case perturbations in order to train against them. And that's a hard problem, essentially because it is both non-convex and severely underparameterized. So we're not in the situation where we're trying to train the classifier, which has a lot of parameters, that has this very nice optimization landscape. We're in a situation where there are a huge amount of local minima. So typically this is done using gradient ascent as a way to approximate the solution of that problem. And that's actually a quite effective solution. It's able to take a classifier that has essentially zero adversarial accuracy to one that has, roughly 45%, which is, like, as far as improvements go, pretty good. The problem is that the cost of increasing that robustness is that we lose into clean accuracy. So when we look at clean data, we are not as good as we were before. So this is one of the issues that we need to deal with, and the typical way to deal with that in classical optimization, right, is to use, or classical optimization theory, balancing this thing, is to use a penalty-based method. So what we're going to do is, rather than training only against these worst case perturbations, we'll just combine both the clean accuracy and this adversarial accuracy into a single loss, mediated by a parameter lambda that essentially weighs those two, and we'll just do what we know how to do, which is to minimize that loss. Right. The main issue with that, though it is very accurate, it is very effective at improving the trade-offs between clean accuracy and adversarial accuracy, is essentially that parameter lambda. Right. For starters, there's no straightforward relation between the value of that parameter lambda and what we are going to achieve in terms of adversarial loss, which is our measure of robustness. So that needs to be tuned by hand, essentially, at that point. That's a time-consuming trial and error, essentially. Not only that, but now the value of that lambda depends on the value of the losses, which depends both on the model that we have, the exact value that we use, and the data set. So if we change the data, for example, we need to not only retrain the model, but retune the parameter, which means changing the problem and changing the model itself. And this idea that it depends on the data also raises some issues in terms of generalization. Yes, we could use cross-validation to do that, and that's typically what is done. But the only guarantee that we have in terms of classical learning theory is that, the aggregated version of this loss generalizes, not that each of the independent parts will hold. So even though it might hold on the data set that we have, how do we guarantee that it holds elsewhere, which is what we are actually trying to solve here, right? Test time. So these are the two issues that we need to essentially deal with, and the proposal, let's say, in order to deal with these two problems or these two challenges is essentially to use constraint optimization to actually write the problem we wrote on top of the slide, right? So in the top of the slide, we said we want to learn a classifier that is robust to input perturbations. So let's write that exact problem. I want to find the most robust classifier, but only amongst those classifiers that have good nominal accuracy. This is exactly the problem that we want to solve. Not only is this a more natural way, in quotes, to write the problem, because now we have formulated an optimization problem that actually represents the word problems, like epistemological problem we're trying to solve, but it also has the advantage of decoupling the performance and the requirements. Right? These things are no longer connected. If I change the data, I need to retrain the model, but I don't need to modify the problem. The problem remains to be the same. It also can be used to deal, we can also use this constraint optimization technique to deal with the first problem that we had in the first place, which is how do we determine these exact perturbations. We can actually replace that maximum by what we call an epigraph form. So now we have an infinite dimensional problem. We say that rather than being strong against the maximum, we want to be strong against each and every one of them. That's an infinite dimensional problem that we can actually use certain techniques in duality and sampling in order to solve using MC techniques. Right? So we can actually deal with both problems using constrained learning and get a solution that is not only better in terms of adversarial accuracy, but also in terms of nominal accuracy. But more important than beating a baseline is the fact that this solution allows us to better trace the Pareto curve that we have, right? What matters here is that there is a trade-off between clean and adversarial accuracy. This is unavoidable. So the question is, can we reach that trade-off? And how do we? This is the typical line with a fixed penalty. This is what you would get. If you use constrained learning, you get something that is actually more efficient than every other position that you have. And the reason for that is, on the one hand, because the dynamics for solving that problem are not by fixing lambda, so there is something else that happens behind, but also because this sampling is better able to explore the dimensions of the problem. So here we are looking at the MNIST. So this is a PCA of the MNIST data set. So you have the first principal component and the second principal component. And what we plot here is for different techniques of finding worst case perturbations, right? We plot their distributions of the perturbations, right? What we can see here is that the method that uses this MC technique is able to better exploit along the first principal component, which we know is the largest variance of the data set. So obviously it's the best direction for us to go to find perturbations rather than the other two, right? Which will waste a lot of energy on other components that are not as important, that we know are not as important. So in a sense, both things together makes it so that we get results that are slightly better than what was achieved before. Okay, obviously there are a few other things that we can do with this that I'm not going to have to talk about, but I'm happy to discuss offline if you are interested in. In terms of supervised learning, there are new definitions of robustness that we have been proposing based still on these ideas of constrained learning, as well as applications in fairness to overcome biases. But also beyond supervised learning, there are a similar theory than what I'm going to talk about today also applies to reinforcement learning. The way we get to this theory is a little bit different, but the idea is that we can use that to both train safe policies, so train policies that are guaranteed to have, say, safe navigation paths. But even more so, we recently showed that there are certain types of behaviors that cannot be achieved using classical reinforcement learning, just as setting rewards, that actually require constrained learning in order to be achieved. So there are certain problems we cannot solve using classical reinforcement. But I'm happy to talk about later. Having said that, it would seem that constrained learning has this property that it helps us learn under requirements. It seems to be useful. So let me explain why I say that this problem is hard, in which sense I mean that this problem is hard, in quotes. So constrained learning, just as unconstrained learning, is often written as a statistical optimization problem, right? Constrained learning is also written as a statistical optimization problem, except one with constraints, right? And this is exactly the source of the, let's say, reason why I would say this problem is harder. And for starters, the first reason is that just as in learning, we don't have access to the distributions under which we are working on, right? So we will want to rely on samples of those distributions only, which raises the questions of whether the solutions of this problem will actually be solutions of the original problem we care about, or at least approximate solutions of the original problem we care about, right? So is it true that if I solve this constrained ERM problem, it would give me a solution of the constrained learning problem that I am actually interested in solving? Turns out this is not always the case. The second thing is that we have to solve now what is a non-convex constrained optimization problem. So in classical learning, we still need to solve a unconstrained non-convex problem for which, we can hope to find approximate solutions by using local methods like gradient descent. And there is overwhelming empirical and practical evidence that actually this is something we can do. Now, because of the existence of constraints, even trying to find a feasible point in this problem could be hard to do. So the question is it true that, so we need to also solve what I would call a computational issue of how then can we go about solving this problem if it were to actually generalize. So these are the two essentially challenges that we need to overcome, and I'm going to spend the next 10 minutes telling you how we go about it, let's say, at least. Not the only solution, but a possible solution. What we have done so far, let's say like this. Right, so let me start with the statistical point. I'm going to ignore point-wise constraints for now, because the theory essentially works the same, and it just means that I have to write more. At the end, I will tell you there is a small difference in that case. When we get to the theorem, I will point out exactly what the difference is. Right? So let's start with this statistical question of, does the solution of constrained empirical problem generalize? So to do that, let me go back quickly. I claimed in my abstract that there was no need for prior learning theory knowledge, so I will give you a primer in 2 minutes. Obviously, completely false, but you know, we do what we get. Enough for today, let's call it like this. You can talk to Ingo if you want to know more. Not me, please. This is all I know about this. So in classical learning theory, like I said, there is this result that is very important that tells us that there is something like, you know, a uniform law of large numbers that happens. When we solve this problem, we minimize this empirical form, we're actually approximately solving a statistical problem, this expected value problem. And this happens for a lot of different models or parameterizations that we can use. For example, you know, linear functions, smooth functions, neural networks, and a large class of those have been shown that something similar holds, let's say. These type of classes of functions are known as, you know, probably approximately correct learnable. This is, in a sense, you can think of this as a, you know, one-dimensional target. We're not going to hit the bullseye ever, but most of the time we'll be pretty close. If you think about it for a second, this is sort of like the best that we could hope to do in this case, right? We have a finite number of samples, so obviously we can't find the solution of the problem exactly, so we're going to be approximately. And those samples are random, so they are drawn IID. So, you know, sometimes we might draw a very bad sample. So obviously it's in probability. So, okay, so I like to joke sometimes that I'm not sure this is a good crowd, but this is like these are like the best you can hope for I'll say an undergraduate student. Typically I say PhD student, but this is the best you can hope for an undergraduate student, right? They'll be mostly right most of the time, and that's good enough. That's pretty good for them. So that's what we expect our models to do as well. So there are a lot of tools that have been developed for doing this, like Rademacher complexity and VC dimensionality, to essentially establish, is this a set of functions for which, let's say, learning is going to work or not? So the question we have is, okay, this doesn't talk about requirements, which is what we care about, right? So essentially what we did is to find a simple extension of PACC by defining this new class of learnability, which we call probably approximately correct constrained learning, so PACC learning, right? So we will require, rather than just requiring to be probably and approximately correct in terms of the objective, we'll have two requirements now. So the first one is that, you know, the solution needs to be near optimal. So we have to be close to the optimal value of the true solution, right? This is essentially what PACC learning does, except PACC learning doesn't have the absolute values around. Right? Now we have a constraint problem. We could do much better or much worse, right? And we want to be close on both sides. That's a distinction without a difference in most cases, but, you know, the definition is that. The other one is that we need to simultaneously be also approximately feasible. So it's not enough for us to be just one or the other. We need to be both with high probability. Very straightforward extension of what happened. Now, obviously, this is a very nice definition, but if we had to spend the next, you know, 50 years rederiving all of learning theory to prove that this is true, that everything that holds for PACC also holds for PACC, this would be somewhat vacuous. It turns out that we can actually show that, well, yeah, two dimensions. We can actually show that, you know, being PACC learnable and being PACC learnable is essentially the same, right? So, and I say essentially for two reasons. First, there is obviously a small difference in terms of sample complexity, because obviously these two things, but it's a log difference, so it's, you know, we pretend that it doesn't matter. And log difference is 6, right? So it's at most 6. I'm an engineer, I said it in the beginning, log is 6 for us. So if So they are essentially the same. The other reason is that what happens, the true result, let's say, is actually that uniform convergence implies both PACC and PACC-C. And therefore, for the 0-1 loss, we get to go back, but it's not a fully commutative diagram, let's call it like this. So that's good news for us because it means that essentially we've answered the statistical problem in the easiest possible way, which is, well, if you could learn before, you can still learn with constraints. So there is no big difference there between these two things. So that's good news for us in the sense that, every problem we could solve, we wish to solve before, we can still solve now by adding constraints. That's good. What it doesn't tell us is how do we go about actually finding solutions to this problem. Right? Again, going back to the problem that this is actually a constrained optimization problem that has a constrained optimization problem that is non-convex. Right? So there are essentially 3 ways to solve constrained optimization problems, convex or non-convex. The first 2 are the ones that are going to be somewhat useless for us, is either feasible update methods or interior point methods. These 2 techniques have a lot of the main advantage that they only give you feasible candidate solutions. So you know that you're always meeting the constraints, and then your problem is just can we optimize the objective within these things, right? The problem for that is that because we have non-convex set of constraints, that's not a really tractable problem. To do projections on that, or, I mean, Frank Wolf is completely out, but to do projections on that or to develop barriers for non-convex functions is a quite complicated problem. Now, the third technique is to use duality. Duality has the main advantage that it's going to give us a very tractable solution, essentially as hard as solving an unconstrained problem, but it doesn't necessarily give us a solution that meets the constraints, right? Because, again, the problem is non-convex, and therefore we don't have this property called strong duality. Now, I said that you also did not need to have any background on optimization, so let me give you the 2-minute primer on optimization. This you can ask me more questions about. This I know a bit better. So, duality in optimization is this property that connects to every constrained optimization problem an unconstrained optimization problem, right? So, which is essentially a relaxation of the original one, right? So rather than writing our requirement as a hard constraint, we write it as a penalty on the cost of the original problem. We then, so this dual problem is actually a lower bound on the value of the optimal one, right? Because it's a relaxation. We then optimize over that lower bound and find the best possible lower bound that we could find, linear lower bound that we can find in the original problem, right? The advantage of that, as I said, is that we actually have to solve an unconstrained optimization problem. So we are back in the situation where we, if we can believe that we can solve unconstrained learning problems, we can solve those as well. That's good news for us. And while in general, this problem is a lower bound, in certain cases, it turns out that these 2 values touch, right? Which we call then this pair as strongly dual pair. Right? This happens, for example, in convex optimization under very mild conditions. What this tells us is essentially, with a lot of stars next to it, but we can replace solving a constrained optimization problem by solving an unconstrained one that is somewhat easier to solve for us. The issue for us is obviously that we're not talking about a convex optimization problem. We have to go over this issue that we don't have strong duality. And to overcome that, essentially, I use a technical discovery that I did during my PhD, that even though non-convex finite dimensional problems, right, they don't manifest strong duality typically, the infinite dimensional does. The infinite dimensional version does. So non-convex variational problems turn out to have very similar duality properties than convex optimization problems, even though they remain non-convex. This is not like lifting, right? So they remain non-convex problems, but they are very similar. So let me give you an example in the context of logistic regression to sort of illustrate what these results is actually saying, right? So if we look at the problem, very simple problem, sparse logistic regression, right? We want to find a classifier that is sparse in the sense that, its parameters have not a lot of zeros. This is not a lot of non-zero parameters. This is an NP-hard problem. This is known to be NP-hard. This is actually very hard to solve. And the typical way to deal with this is that we are going to use a relaxation, a convex relaxation. So we will replace this sparsity by the closest convex envelope that we have, which is the L1 norm. And this means that we go from a non-convex to a convex problem that we now can solve. So the barrier of complexity here is between non-convexity and convexity. And there's all this theory in compressive sensing that actually tells us that we can sometimes recover the solution of the problem on the left, which is the one we actually care about by solving the problem on the right. Now, what I'm going to say is that there is a different barrier that we can exploit here, which is that even though discrete sparse logistic regression is NP-hard, the continuous version of it is not, right? It's still a non-convex problem, but it is actually tractable. So here, the barrier of complexity is not between convex and non-convex. These are two non-convex problems, but it's between being discrete or being continuous. Right? And these results come from some theorems from vector measure theory. They are like the Shapley-Folkman lemma of continuous versions, if you've heard of that. But the intuition, or like a caricature of this result, is that the integral turns out to smooth out the non-convexity. It's really caricatural, but it works super well actually in practice. If you have any non-convexity, just shove it into integrals, you're good. Essentially, that's what it means. Then there are a lot of asterisks next to this claim, but it works pretty well. And you can do not only EEG classification with this, which is like sparse logistic regression, but you can actually do there are a lot of different applications of this result that we have exploited, essentially creating this new class of optimization problems, which are the sparse functional problems that we can actually go about solving, and they have a lot of applications. For what we are talking about today, what this result tells us is that even though we cannot relate this empirical dual problem to the original empirical constraint problem we want to solve, we can actually directly relate it to the original learning problem we want to solve, which is the statistical problem. Right? So even though neither these two optimization problems that we're looking at, they are not related to each other, they both provide solutions to the statistical problem that we actually care about solving. Approximate solutions and probably provide solutions, right? So this is always the little caveats that come between what we call solutions in this case. And again, the intuition here is the same as I said before. It turns out that all these losses are inside integrals, right? And under mild conditions, that means this problem is strongly dual. And if this problem is strongly dual, we can then, through perturbation theory, connect it back to the original problem that we care about. So let's look at the exact result now, because I have been talking in the air for an hour, and you don't have to believe things in the air. But so what I'm going to say is that essentially if the parameterization that we are using is a good covering of the underlying space of functions that we're talking about. So for example, in the case of neural networks, is the space of continuous functions, right? Or in the case of kernels with, let's say, a finite number of combination of kernels is some RKHS, right? Is it a good covering of this problem? And if it is a good covering of this space, then essentially what we are saying here holds, and that this dual problem is actually a PACC learner or near PACC learner, in the sense that it will provide solutions that with high probability are both near optimal and approximately feasible. There is one thing that I mentioned in the beginning that I had to say, is that in the case of pointwise constraints, we need these losses to be convex. The parameterization can be nonlinear, so the problem can still be non-convex, but the losses have to be convex in this case, right? Otherwise, because this thing is not inside an integral, things get a little bit tricky. But for problems that don't have pointwise constraints, actually the loss can be non-convex as well. So it's interesting to dig a little bit into this error so that we can see where they are and why I'm saying near PACC here and where does this universality thing comes in, right? So there are essentially two sources of error, as in unconstrained learning actually. We have two sources of error here, the estimation and the parameterization error or approximation error. So the first one is comes from this richness of the parameterization. If it's a good covering of the space of functions, then this error becomes very, very small. Right? Now, good coverings of functions, good parameterization, rich parameterizations, let's say, they typically use more parameters, which means that, we're going to have an increase of some complexity. Here I'm talking about complexity in terms of VC dimension, but it could be another measure of complexity as well. They'll have an increased complexity, which means that we then need more samples to get a smaller estimation error. Right? Now, the only difference here that is interesting to note is that only the near optimality is affected by this complexity. Right? As long as we can find, there exists always a solution that is feasible in the problem that we're solving. It just might not be a good approximation of the near optimality. Now, increasing the number of parameters, this trade-off is one that is typical in classical learning, right? It's this sort of parameterization, bias variance trade-off. Here, however, it's mediated also by the complexity of the problem itself. So how hard is it to meet the requirements as measured in terms of some sensibility, in terms of optimal dual variables, also affects how many samples we need. So now, rather than having this sort of two-way trade-off that we have between parameterization and sample size, right? We have now this three-way trade-off between both the parameterization and sample size and the difficulty of the requirements. Easy requirements require less samples to impose than harder requirements. That's essentially what it says in the case of constrained learning. That's something that we did not have in classical before. Now, this is all and good, but even though I told you that it is possible, the question remains of how is it possible to do. Right? So, to answer that, we are going to go back to duality exactly. Right? So the way we do that is by using, I write Primal-dual, or I actually mean dual ascent. Right? So what we're going to do is essentially doing a form of alternative minimization. So we'll tackle first the inner problem, which means we will fix everything, which in this case is lambda, and just solve this inner problem that you should recognize is just a regularized DRM problem. That's what everybody has been doing to solve the problem in the beginning that I mentioned, right? So this is a problem that we actually, have become good at solving by using, let's say, gradient descent, right? There are a lot of empirical and theoretical evidences that, gradient descent will find good minima for this problem. Perhaps not the optimum, but something that is good. Our second step is going to be to solve the outer optimization problem, which means that we will update the value of this lambda by using the constraint violation. Right? So we will take, if we are violating the constraint, then we will increase this value. If we are not violating, then it will be decreased. Right? And the value of lambda, however, here that is important to note, is actually, because it is in this update, is actually the accumulation of the history of violation of the problem. It is not only about the value that we are violating right now, but throughout the problem, how much we have violated. We essentially have like an integral controller if somebody if there are electrical engineers here. So we can think of this as essentially, a sort of adaptive regularization parameters, right? Adaptive regularization solution. There's obviously something somewhat deeper going on here that actually allows us to show that if we can find an approximate solution to the inner problem, something that we believe we can do using gradient descent, then we actually are guaranteed to converge to a neighborhood of the optimal, right? Because this is also an adaptive regularization method, but it's also a gradient ascent method. Underneath this, there is a gradient ascent procedure. Obviously, we can't run the first step ad infinitum. That would take, well, infinity. So what we do is actually that we truncate it at some point, and then we'll run the dual method in a lower time scale. So we'll update the dual variable, say, once per epoch. That's typically what we do. And doing that means that we get to a solution that is essentially, let's say the pseudocode is essentially the same as the one we use for training today. If we remove step 8, that's exactly stochastic gradient descent. And the only thing we need to do is once in a while we need to update the dual. So it's actually very small, let's say, modification of the problem, right? Now, the thing that is important to note here is that the output of this problem is actually two things. First is the solution that you want to your problem, the parameters, but it's also the dual variables, and the dual variables have a lot of information into them. Among other things, it is sort of the result of this accumulation of violation history, right? The one thing that I sort of want to contrast for a second here is the difference between, penalty-based and dual learning. Right? So in the penalty methods, we are going to fix lambda, which is a data-dependent parameters, and the guarantees that we are going to get are essentially with respect to disaggregated loss. Now here, the parameters that we're going to fix are actually C. That's a parameter that depends on the requirement. Lambda is, let's say, a hidden variable that we use to solve the problem, but it's not the parameter that we set per se. And this means that by doing that, we actually get to give generalization separately, jointly, let's say, in terms of the loss and the penalty violation, right? Not only that, but the type of results that we get are very different. So if we look at, this is the, let's say, Pareto curve between nominal and adversarial accuracy. So Pareto curve, just a trade-off curve between nominal and adversarial accuracy. We see that the different values that if we set different values of C or different values of lambda, the solutions we get are very different. Setting different values of lambda, fixed lambdas, right, just navigates really closely to the solutions that have, you know, a certain level of adversarial accuracy, maybe a little bit better nominal accuracy than others, right? By changing C, we get to actually navigate this, let's say, space of different possible solutions that we could solve much more effectively than we would in the other case. And what that happens is that, I had a nice video that we are not going to see, but essentially what happens is that the value of the dual variables actually changes as we are solving, and these dynamics are as important to the solution that we get at the end than, you know, the actual value that it has at the end. So during the first phase of training, what happens, again, this is as the adversarial loss is decreasing, right? The strength of the adversarial, which was essentially the value of the dual variables, right, increases until a certain point where we meet the requirement that we had set, which in this case was 0.1. And after that, they start decreasing. And they essentially start decreasing until it reaches a value that is essentially 0 at the end. Right? So if we had set the dual variable to this value, which is 0.5, we would not have achieved the solution that has, you know, that meets the constraints, because actually the dual variables need to go to very large values to drive your model to regions of the set where those actual robust solutions are, and then you can use very small. So this is something actually that is an empirical observation that has been made many times, that, you know, we need strong adversaries only in the beginning of training for many reasons. What is important here is that this is a behavior that arises naturally from the algorithm that we are used to solve the problem. So the exact value that it needs to go to in order to meet the constraints, or the exact value that it needs to have at the end, comes from these dual dynamics that we are using, these primal dual dynamics that we are using to solve the problem, and it's not something that we need to set ourselves. Right? What that means as well is that if we were to, just to sort of give another intuition, is if we were to take this model that we obtain at the end of training and continue training it just regular, just with the clean data, right, would actually get a model that is better than the one that we would expect, right? So this is the unconstrained solution. So that would be if we set lambda to 0 from the beginning, right? And if we were to warm start it, so take the solution that we get at the end and then train with just clean data, we get a model that obviously is worse than the constrained model in terms of robustness, but turns out to be much better than this model that starts from 0, let's say. And this is something that we know nowadays theoretically a little bit better, because there are a couple of results that show that, you know, randomly initialized neural networks are not robust, very, very likely to be not robust, and that gradient descent by itself tends to drive models to non-robust regions. Right? So the reason why we need these very large dual variables in the beginning is that to bias the model towards robust models is something that is not trivial, straightforward to do. Anyway, so to summarize essentially what I have talked about today, I hope that I have managed to convince you that first, constrained learning is, okay, A2, perhaps the right was just me being a bit American in the beginning, like really boasting, but it's a tool to learn under requirements. And it's definitely one that allows us to impose generalizable requirements that happen naturally during training. Right? It's not something we need to do on top of training a model. It is, on the other hand, a problem that is somewhat hard because it is a constrained non-convex statistical optimization problem that we need to solve. But it turns out to be one that is very close to the learning problems that we solve today. So essentially, we can learn under requirements whenever we can learn at all today. And how we do it is actually by solving penalized DRM problems. By which I mean, it turns out that we can do learning under requirements just the way we do learning today. You just need to be a little bit smarter about how you do put things in the right places, right? So we could, in a sense, we could be doing learning, constrained learning, the way we do today. I mean, maybe that's a good idea for us to be doing, by the way. That's where I want to go with this. There are a few things that I couldn't mention in this talk, I think that are interesting to mention. Obviously, there are other applications that I have mentioned, the different forms of robustness, fairness. Other things that we have been working on recently are invariance, smoothness, and how to incorporate prior models or prior knowledge that we have into this. This is actually something that I think would be very interesting to develop here, this idea of prior information into learning. Constraint reinforcement learning is another point that is somewhat parallel theory that has grown. It uses different techniques, but very similar results apply in that case. As I mentioned, I think gradient descent ascent dynamics, so that algorithm that I wrote essentially, right, there are a lot of things that we don't know about it. We understand very well gradient descent in over parameterized settings and in different types of statistical problems. But gradient descent ascent is first a very different and more complicated dynamics that we understand less well in these settings. I think this is something very interesting, something we've been working on a little bit, and there are very different behaviors that we can do, that actually arise in those dynamics, right? In those sometimes games, I think is something that people like. I don't like to call it games, but they are games. That's just my own bias. There's also some work that more recently that continue to be ongoing on constrained estimation and control. So both on functional sparsity has to do with these SFPs that I mentioned earlier. Non-submodular optimization is something that I did earlier, risk awareness, and graph signal processing and graph neural networks, which are essentially, if I had to think of a constraint, is more of an invariance constraint with respect to some network that is not necessarily, these regular networks that we have, like in an image, for example. We want to be invariant into a more irregular network of some sort, like in recommendation systems or something like that. So I think that this research, the way I see it, is really takes us from this idea of artificial intelligence that is supposed to arise implicitly from things that we are doing, to one of engineered intelligence that actually does the things that we want it to do. Right? I think that looking forward a little bit, like more in terms of long-term vision, I think that constraints, we are due a new breakthrough in learning, and I think that constraints could certainly help us, take part into this, would certainly help us take learning into more of these systems engineering sort of applications where I think there is a lot of powers for us to build. Obviously, this is not work that I did by myself. These are collaborators of mine, both at Penn and elsewhere. And and if you want to learn more about this, you can check it out on my website, or feel free to send me an email, or we can just talk since I am here now. I think I have still a few hours of not sleeping ahead of me from the jet lag, so maybe I can still say some somewhat smart things, perhaps. After that, I have no promises, so thank you very much.